We started off this chapter with some simple area formulas. The formula for this section is not hard, but applying it can sometimes be tricky. Before we get to the formula though, this postulate is thrown into this section. Seems like if you're going to bother with it at all, it should be with the first area section, but oh well. It shows up here. It shouldn't be earth-shattering. Like most postulates, it is so basic and obvious that it should give you the well duh reaction. If two shapes are the same size and the same shape, then of course they will have the same area. Not much to say with this. Moving on to the major point of this section. Before we can get to the formula, we need to get some vocabulary down first. This section deals with regular polygons, and all of the polygons in this page are regular polygons. The first vocab word is the center of a regular polygon. As you can imagine, the center is kinda, well, in the center. Here are all the centers for these regular polygons. Sometimes people think the pentagon center is a little low, and often the majority of students will end up feeling like the triangle center is a little too low. But I assure you they are correct. By definition, the center of a regular polygon is the center of a circumscribed circle. So it might help if I drew in all of the circumscribed circles for all of these regular polygons. Once the circles are drawn in, the centers usually look like they aren't too low anymore. Anyways, that's the center of a regular polygon. You have seen the radius of a circle a ton, but regular polygons also have a radius. What do you think is the radius of a regular polygon? Where do you think we should draw it in? Let's play a quiz. Which of these pictures do you think depicts what a radius, or radii, of a regular polygon is? Do you think it is the one on the left? The one in the middle? Or is the one on the right correct and they are all radiuses? Do you remember how we defined the center of a regular polygon? It had something to do with a circumscribed circle. The same thing is true here. Let me draw in the circumscribed circles. Does that change your answer at all? The radius of a regular polygon is the radius of the circumscribed circle. So that means the one on the left was the correct answer. That one is also the radius of the circumscribed circle. The next vocabulary concept is the central angle of a regular polygon. The central angle kind of sounds like it comes from the center, and that part is true. The vertex of a central angle is the center of a regular polygon. All of the angles on this page have their vertices at the center. But are they all central angles? Quiz time again! Do you think the one on the left is a central angle? Maybe it's the one in the middle. Or is it the one on the right? Or option 4, are they all central angles? What's your guess? Do you have one? When I pose this question to students, the fourth choice is usually the most popular. Most guess that they are all central angles. Sadly, that's not right. So with that option now gone, what's your guess now? The answer is the one on the right is a central angle. The reason has to do with the definition. A central angle of a regular polygon is formed by two radii drawn to two consecutive vertices. With that definition, the one on the left doesn't count because those two radii aren't drawn to consecutive vertices. The two vertices need to be next to each other. The one in the middle doesn't count since it is only formed by one radius. The other side isn't a radius at all. The one on the right is the only one formed by two radii going to two consecutive vertices. The whole reason for this specific and restrictive definition for a central angle is so that there is only one possible size for each central angle. Let's see exactly how. I am drawing in all of the radiuses of all of these regular polygons. By doing that, all of the central angles are drawn. The pentagon is split up into 5 central angles, the hexagon into 6 central angles, and so on. Since we force central angles to be to consecutive vertices, we know exactly how big they are. It is 360 degrees to go around a full circle, but look at the pentagon. That 360 degrees has been split up into 5 equal parts. So each central angle there must measure 72 degrees. For the hexagon, the 360 degrees is chopped up into 6 equal pieces, so each one must measure 60 degrees. That same logic works for the last two also. In general, we know that the measure of a central angle of a regular n-gon is always 360 divided by n degrees. Being able to find the central angle will help when we get to the area calculation. Our last vocabulary word is one where the pronunciation is a bit weird. It is kind of like this famous one from the internet. Most people, when they see .gif, pronounce it as GIF. It makes more sense to people that way, and it is by far the more popular way to say it. It's supposed to be Jif, like the peanut butter. So there's a big internet debate about whether you should pronounce it the popular way, GIF, or the way it was supposed to be, GIF. Getting back to geometry, this vocabulary word, when most people see it, want to say APOTHEM. That's clearly the more popular way to go. People seem much happier with it that way. Kind of like GIF. But that isn't the correct way. It's supposed to be APOTHEM. That's the correct way to do it. So that's what I will do. But despite me saying all that, APOTHEM always seems to be the more popular way students like to go. When I hear students say APOTHEM, I always get the image that they are saying opossum with a lisp. Oh, that APOTHEM is so cute. And that's about as cute a picture of an opossum as I could find. Those are not pretty creatures. They really are huge rats. But every time I hear APOTHEM, it really does sound like a possum with a lisp. And now that I have said that, some of you will be even more hell-bent on saying it like that. Ah well. Time to get what an apothem actually is. The apothem is the perpendicular line segment from the center of a regular polygon to a side. One of the 6 apothems has been drawn in on this hexagon. And now we get to the formula. The area of a regular polygon is half the product of the apothem and the perimeter. Area equals 1/2 AP. There are 2 a's in the formula. Capital A is the area, lowercase a is the apothem. Not a complex formula, but it sometimes takes some work to get the pieces you need to plug into the formula. Generally speaking, whenever you are tasked with finding the area of a regular polygon, and you need to use 1/2 AP, then you almost always need to draw in much of the vocabulary we have been talking about. Find the center. Then draw in a radius. I will note here that the radius bisects one of the interior angles. Therefore, you know that these 2 angles are congruent. That will be helpful here in a bit. Next, we need to draw in an apothem. The apothem is also a bisector, but this time it is a segment bisector. It cuts one of the sides of the regular polygon in half. That is also used a lot. We now have made a little triangle. This triangle is absolutely key to solving these types of problems. If you're going to be using 1/2 AP, you should immediately draw this little triangle in if it isn't already drawn in for you. It is the key to the problem. You'll almost always need to fill in the angle measures of the little triangle. We have one 90-degree angle from the apothem, but we need to find the other 2 measures. You have 2 options in order to find the missing angle measures. The first option is to find the measure of a central angle. That may seem odd since there isn't even a central angle in this picture, so let me draw in one more radius to make one. Here's a central angle. You may notice that the apothem has bisected the central angle. It cuts it in half. So even though our little triangle here doesn't have a central angle, if you do find the measure of a central angle, this angle is half of a central angle. Very handy. And the central angle calculation is easy. It's just 360 divided by the number of sides. That's why I went over the central angle calculation earlier. This is when it is used. Once you have filled in that angle measure, then simply subtract it and 90 from 180 to find the missing angle. That's option number 1. Option number 2 is to find the measure of one of the interior angles. You have to think back a bit, but that's the formula. It certainly isn't as easy as option number 1, as the central angle calculation is easier, but some students prefer to do it this way, and it's perfectly fine if you want to do it. So if you calculate one of the angle measures, and the radius cuts one of them in half, you can fill in the angle measures of the triangle. It's a little harder than option number 1, but definitely a possible way to do it. So when we go about using 1/2 AP, there are 4 possibilities of what will happen. I'm not going to go into full examples of each case, but I will show you the key part of what will happen. Our first case is an equilateral triangle. Like every one of these problems ever, we will want to draw in the key little triangle to help you solve the problem. You will need to find the missing angles, so you have 2 options. If you go for option number 1, the central angle measures 120 degrees. If you cut that in half, then you know this angle is 60 degrees. From there, you can fill in the missing angle. If you go for option 2, then you will see that one interior angle is 60 degrees. And the radius cuts that in half, so this one is 30 degrees. Either option will let you figure out our little special triangle is a 30, 60, 90 triangle. Your favorite. That's the first case. The second case involves a square. I'll go through this one quicker now that you have a feel for it. You still need that special triangle drawn in. From here you have 2 options. Either of the options will let you figure out that you end up with a 45, 45, 90 triangle. Another special triangle. That's what happens in the second case. We are skipping pentagon, and the third case is a hexagon. Draw in the special triangle first. Now fill in the other angle measures using whichever method you prefer. You will end up finding that we once again have a 30, 60, 90 triangle. Those suckers keep popping up. The only difference is that the 30 and 60 have switched spots compared to the equilateral triangle. This is the third case. The fourth case is all the rest of them, pentagons, octagons, or whatever. The equilateral triangle, square, and regular hexagon all end up with special little triangles. They are easy to work with. They simply work all nice and neat. But if you are working with any other polygon, then things won't end up so nice and neat. I have a pentagon here to show you what happens, but I could just as easily have used a decagon or any of the others. The same kind of thing will happen with all of them. Just like the rest, we do need to start out with our special little triangle. And you have the same second step. You still need to find the missing angle measures. But after all is said and done, we end up with a special little triangle that isn't so special. It isn't a 30, 60, 90 or a 45, 45, 90. All of the other polygons end up with little triangles where you end up needing to use SOHCAHTOA to approximate the lengths of the apothem and the perimeter. That's the nature of the beast. So be happy when you start off with a triangle, square, or hexagon. They all end up with special little triangles and easier paths to find the final answer than all of the others, which require trig to get there. This is a lot of talking for one simple formula, 1/2 AP.